Hi, and welcome back to DATQVAULT video lectures. In this video, we're going to cover second order substitution reactions. So, substitution reactions are pretty much exactly what they sound like. Here we have a general substitution reaction scheme, where we have a substrate with a good leaving group, and some sort of a negatively charged nucleophile with a lone pair of electrons. In a substitution reaction, these electrons will attack the carbon center, bearing the leaving group, and then the leaving group will leave to get our substitution. So now the nucleophile is bound to the carbon center, and the leaving group is away from the carbon. There are two different types of substitution reactions. The first type of substitution reaction is an SN1 substitution. S standing for substitution, N standing for nucleophilic, and the 1 standing for first order. In a first order or SN1 style substitution reaction, we form a carbocation intermediate, and because we form a carbocation intermediate, only secondary and tertiary carbons are used in the SN1 style mechanism. This is because only secondary and tertiary carbocations are stable. SN1 style substitutions are not stereospecific, which means the stereochemistry in the reaction is not retained. In the SN2 style substitution, the 2 stands for a second order reaction. We'll go over why this is in the reaction kinetics. In an SN2 style substitution, there is going to be no carbocation intermediate, and because there is no carbocation formed, we're only going to be using primary and secondary carbons for this reaction. SN2 style reactions are stereospecific, and they are stereospecific because they go by an inversion of stereochemistry. In this lecture, we're going to focus only on the SN2 style substitution reaction mechanism. There is another lecture that focuses specifically on the SN1 style substitution. Alright, so what does the SN2 style reaction mechanism look like? So in a substitution, we have a substrate with a good leaving group and some sort of a good nucleophile with a lone pair of electrons. The first step in the substitution reaction is the attack of the nucleophile on the carbon bearing the leaving group. It's important to note that in the SN2 style reaction mechanism, the nucleophile actually attacks the carbon bearing the leaving group at the same time that the leaving group is breaking its bond with this carbon. This explains the reaction being second order or bimolecular because two molecules are involved in the formation of the product. So once the leaving group fully leaves and the carbon nucleophile bond is formed, we get our substitution product and we get our leaving group. If you notice, this reaction goes by inversion of stereochemistry. This is because the nucleophile attacks the carbon from the opposite side of the leaving group, forming this intermediate, and then once the leaving group leaves, the nucleophile is then on the opposite side of the carbon. These R groups all move this direction, and the center around the carbon is then inverted. So if the stereochemistry around this carbon was initially R stereochemistry, once the nucleophile attacks and we get our product, the stereochemistry around that carbon center is going to have the opposite stereochemistry, so it's going to be S stereochemistry. So this reaction is what's known as being stereospecific. So the nucleophile attacks and creates only one specific enantiomer after the reaction happens. The reaction is stereospecific because it goes by inversion of stereochemistry. So the stereochemistry is inverted from R to S stereochemistry because it attacks the carbon center from the opposite side that the leaving group is going to leave the carbon center. So the reaction rate of an SN2 style reaction are governed by three major things. The first thing is the size of the R group, which is directly correlated to steric effects. The larger these R groups here are on the carbon, the slower the reaction is going to be, which mainly means that the nucleophile is going to have a harder time getting into this carbon center to actually push away this leaving group if these R groups are larger. SN2 reactions can go with either primary or secondary carbons. A primary carbon will always undergo an SN2 style reaction mechanism because the carbon is basically not hindered at all. There's kind of some gray area here with a secondary carbon. Secondary carbons can undergo either primary or SN1 or SN2 style reaction mechanisms. The smaller these R groups are for a secondary carbon, the more likely it's going to undergo an SN2 style reaction mechanism. The larger you make these R groups, the more it pushes towards an SN1 style reaction mechanism, which is going to form a carbocation intermediate. When you go to take the DAT, they're probably going to make it so where there's not any gray area whatsoever in these questions. So usually you're going to see an SN2 style reaction mechanism involving just a primary carbon. Another thing that governs the reaction rate of an SN2 style reaction mechanism is the stability of the leaving group. So the more stable this leaving group is over here, the faster the reaction is going to go. And that's directly correlated to the ability for the leaving group to stabilize this negative charge. So, for instance, if our leaving group is some sort of a halogen, iodine is going to be a better leaving group than bromine, which is going to be a better leaving group than chlorine, which is going to be a better leaving group than fluorine. And of course, this is directly attributed to the fact that iodine is a larger atom, it's more polarizable, and it can better stabilize the negative charge once it leaves. Also, the reaction rate is governed by the strength of the nucleophile. So the stronger this nucleophile is, the faster the reaction is actually going to happen. You can determine the strength of a nucleophile more or less based on the stability of the nucleophile. A less stable nucleophile is going to want to attack this carbon center faster. Also, the size of the nucleophile is going to govern the reaction rate. So a much smaller nucleophile is going to be able to attack this carbon center a lot faster because of decreased steric hindrance, and is going to be able to basically just get in there and attack that carbon center as the leaving group leaves. Alright, so let's try to answer a DAT style question on SN2 style reaction mechanisms. So in this question we're asked what the product is of a reaction with R2-chlorobutane and potassium cyanide. So why don't you pause the video, take a second to answer this question, and then we'll answer it together. Alright, so on the DAT, if you're asked a question like this, you're probably not going to know whether it's going to be an SN1 or SN2 style reaction mechanism. Like I said, you're probably not going to see a question like this that has so much gray area, but if you do, we'll figure out a way to reason through this being either an SN1 or an SN2 style reaction. So first, I'm going to draw 2-chlorobutane. I'm not going to draw stereochemistry just because we want to figure out if it's going to be SN1 or SN2, and stereochemistry isn't going to really matter in this case. So here we have 2-chlorobutane, and we have potassium cyanide. We notice that 2-chlorobutane is relatively unsterically hindered, as these two R groups contain methyl and 2 hydrogens, and over here we just have a methyl group. Also, we notice that our nucleophile in this reaction is cyanide, which is relatively small. It's actually very small compared to most nucleophiles. and cyanide is a very strong nucleophile. So it's going to be able to get to this carbon relatively easily to push off this chlorine. Also, chlorine, when we look at all the halogens as leaving groups, is a relatively poor leaving group with respect to bromine and iodine. So it's actually going to favor an SN2 style reaction because of this, and not an SN1 style reaction. So because of these factors, the strength of the nucleophile, the steric hindrance around this carbon, and the stability of the leaving group, we're going to say that this is going to be an SN2 style reaction. Alright, so now that we've determined this, we can draw our product for this reaction, and it's going to be some sort of 2-cyanobutane. If we look at our answers over here, we only have 2 of them that represent 2-cyanobutane. So if we start with this stereocenter being R, and we do an SN2 style reaction, we know that SN2 reactions go with inversion of stereochemistry because they attack from the opposite side that the leaving group leaves. So if this happens, stereochemistry around the center is then going to be S. So our answer is going to be B, which is S2-cyanobutane. Alright, so just like I emphasized in SN1 style reaction mechanisms, kinetics in SN2 reaction mechanisms, being able to understand this is going to be extremely important on the DAT, as kinetic questions come up all the time. So here on the y-axis we have energy, and on the x-axis we're just going to have some sort of a reaction coordinate. The first step in an SN2 reaction is the attack of a nucleophile on the carbon. So if we do this, we get this transition state up here where the leaving group is leaving, so in this case the carbon-bromine bond is being broken. At the same time, our nucleophile carbon bond is being formed. In this case, our nucleophile is just a generic hydroxide anion. So this transition state is, of course, much higher in energy than our starting material. This reaction being SN2, the 2 standing for bimolecular or second order, means that both the nucleophile and the starting material are involved in forming our transition state. So this reaction is bimolecular. This is because no carbocation is being formed before the nucleophile is attacking the carbon. The leaving group and the nucleophile are both interacting with the carbon center at the same time to form this transition state. So once the bromine-carbon bond is fully broken and the oxygen-carbon bond is fully formed, we get our products, which are lower in energy than our starting material, which actually completes the reaction coordinate for the SN2 reaction. It's actually relatively simple, but the key points to remember for the kinetics of an SN2 reaction are that their overall rate is dependent on both the nucleophile and the starting material, in this case bromomethane. And of course, you're multiplying it by some sort of constant, rate constant, which is K, which is dependent on things like the strength of the nucleophile and how good of a leaving group the leaving group is on the substrate. Alright, so let's answer a DAT style question on the kinetics of an SN2 reaction. So why don't you go ahead and pause the video for a second, answer this question, and then we'll go over it together. Alright, so in this question, we're asked which of these statements is false about the following reaction. So we have to notice that, first of all, that this is going to be an SN2 style reaction mechanism. And that's because A, the substrate is a primary halogen. We have a very strong, relatively small nucleophile in ethoxide. So let's start eliminating some of these questions as being either true or false. I'm just going to write out A, B, C, D, E for all the questions, and then we're going to put either T or an F next to them based on whether I think it's the answer is true or false. So based on this reaction being SN2, if we increase the concentration of iodobutane, does this increase the reaction rate? So SN2 reactions are bimolecular, so the reaction rate is dependent on both the substrate and the nucleophile. So yes, this is true since this is the substrate, and if we increase the concentration of it, yes, we do increase the reaction rate. So answer B, is this reaction second order? So since we determined based on the nucleophile and the electrophile in this reaction that this reaction is SN2, the 2 stands for being second order. The nucleophile and the substrate are both important in forming the transition state. So yes, this reaction is going to be second order, so that statement is true. C, elimination is a competing reaction. We didn't cover this, but in all substitution reactions, if you have a strong base, elimination is always going to be a competing reaction in a substitution reaction. This is because we have a strong base and we have an alpha hydrogen over here, which can then eliminate the iodine. So elimination is always a competing reaction in a substitution when a strong base is involved as a nucleophile. So that statement's true. D, the reaction is unimolecular. We already determined in question B that indeed it is true that the reaction is second order, which directly contradicts that the reaction is unimolecular, so that has to be false. And then increasing the concentration of our nucleophile sodium methoxide increases reaction rate. The reaction is second order, which means the formation of the transition state is dependent on nucleophile and the substrate. So yes, increasing the concentration of sodium ethoxide is going to increase the rate of the reaction, so that's true. Our only false statement, which directly contradicts B, is D. So our answer is going to be D for this kinetics question about SN2 style reactions. So I suggest right now that you go and you answer some questions on SN2 reactions, and then hopefully that'll solidify what you've learned about SN2 reaction mechanisms.